In this next example, we want to look at a switching circuit. So in this circuit, the switch has been at position X for a very long time, and then at t equals 0, it moves to position Y. So a little bit of a review of what happens when switches have been in position or circuits have been hooked up for a very long time. As you recall, basically capacitors become open circuits. And so basically between these two terminals, our V sub C, which is going to be the initial condition on the capacitor. For t less than 0, that capacitor looks like an open circuit. So all of the 100 volts is going to appear across the capacitor. So just to kind of have the picture in front of you while we talk about this. So now let's look at how we go about solving this using Laplace techniques. So we're going to apply the same methodology, and so obviously step 1 in that method is to determine the initial voltage across the capacitor. Now let's go back and look at that figure one more time. In this example, it's very, very easy to find the initial condition. You don't really even need to resketch the circuit. You can do it in your head. Had this been a more complicated circuit, what I would do is I would take the part of the circuit that's active for t less than 0, redraw it, not considering the other part of the circuit, because to me it just causes confusion. And then I would calculate the initial conditions, which sometimes is going to be a little more difficult calculation than this one. Okay, so back to that. We already determined that our voltage across that original capacitor, our initial condition was 100 volts, so that's going to be important. We also know that for t greater than or equal to 0, there were no voltage or current sources in the circuit, so we don't have to worry about transforming voltage or current sources. So t greater than or equal to 0, this connection is made, and now you have this half of the circuit. This source for t greater than 0 is out of the circuit, so you're only dealing with the capacitor and 3 resistors. So here we go. All right, so we want to resketch the circuit, which means the first thing we have to do is we have to input the equivalent for the capacitor. Now remember from our figure and our table that that's going to be a capacitive impedance, which is given by 1 over SC. And so when you simplify that, you can write that as 2 times 10 to the 6th over S. So this is our 1 over SC term. And then remember, this is our V sub 0, our initial condition. And I won't say V sub 0 because that's a different thing here. So this is our initial condition on the capacitor divided by S. So it's basically a step function voltage. I'm sorry, my pad is a little trigger happy this morning. All right. So that's the equivalent for the capacitor. If the capacitor had no initial conditions, the source, in other words, if it had an initial a voltage at 0 minus of 0, then this source would not need to be present. It would have a 0 value. But as we know, it did have an initial condition, so we'll put 1 over S here. Okay, and so the next thing is to realize that the impedance of the 3 resistors is given by their resistance when we transform the circuit, and the capacitor, we just talked about that. So here's the capacitive impedance. Here's the value of the source voltage that's in series with it. So this is our S domain circuit, and now we're just going to solve this circuit like we would any other circuit. We've got a voltage source, we've got 2 impedances, and then we've got 2 impedances in parallel. So the first thing that was done was the 240 and the 60 kilo ohm resistors were combined in parallel. So let's go back and look at that again. So here's that circuit. These two were combined in parallel. That's going to preserve this voltage V sub 0, which is what we're actually solving for. So that's probably a smart idea. So those are combined in parallel, and then that's going to put all 3 of those elements in series. So you can use voltage divider. So here's the resistor that we combined that we want the voltage across. Here is the capacitive impedance. Here is the other resistor. And then here's that resistor. Remember, when you do voltage division, you can do that across a series string. So you can do voltage division even if you have 4 or 5 elements. If they're all in series, you can still do voltage division. And then this 100 over S, that's the voltage source across all 3 in the string. When you simplify that, you end up with 60 over S plus 25. Now, step number 6, where you use initial and final value theorems to show the initial value and final value would be reasonable. I have to be honest, this is not a step that I ever do. If you want to do this as practice on initial and final value, that's fine. I just go ahead though and take the inverse transform, so that I kind of think that's the reason the author's doing this. In reality, you don't really use initial and final value theorem for this purpose. They're used primarily in controls to look at things like an error that you might have introduced into a control system. So let's go on then. What we're going to do is we're going to take the inverse transform of this expression. And when we do that, we have 60 e to the minus 25t u of t. Notice that we have this u of t in here because if we just had 60 e to the minus 25t, that would exist before 0, which is actually not the case. This circuit exists only for t greater than or equal to 0. So that is the voltage V out. And I believe that concludes this example. Yes, it does. So here's another example. Now I'm going to talk more about RLC circuits. I'm going to do a special, I probably won't do a video. I'll probably do a write-up on RLC circuits and have you do just a little bit of a mini project on that, because they're interesting and they're used for a specific purpose. This RLC circuit is a parallel RLC, so everything is in parallel. And this switch was closed for t less than 0. So I'll just go ahead, put a line here, and we'll think about the t less than 0 circuit. So when t is less than 0, we have a short here. All of the current will go through the short. Okay, this doesn't make any sense. Oh, okay. We're also given that an initial condition across the capacitor is 50 volts. And an initial current in the inductor is 29 amps. Okay, this is kind of a weird problem, but we'll just take their word for it. And so then the switch opens at t equals 0. The truth is, if the current is flowing and it's under DC, yeah, I guess that's okay. All right, so anyway, the switch opens at t equals 0, and we're going to be left with these 3 in parallel. What we want to do is find the voltage here, given that we have an initial condition on the current in the inductor, an initial condition in the voltage across the capacitor. I'm going to have you just ignore this, because given that they give you the initial conditions, you don't need to actually try to find those. Now, when the switch opens, okay, then things change. All right, so when the switch is closed, this entire 24 milliamps flows through this short, meaning it doesn't really enter into the circuit. So you've got the circuit, you've got these initial conditions. Then what happens is you open the switch. So let me get my eraser. When you open the switch, now all of a sudden this 24 milliamp source becomes relevant. I actually would have put the switch in a different place, but that's okay. Okay, so now the 24 milliamps becomes relevant when the switch is open, and so you had these initial conditions, but now the 24 milliamps is turned on, so some things are going to happen. It's going to have to enter into the circuit for t greater than 0 because it's no longer shorted out. So the 24 milliamps comes into play for the t greater than 0 circuit. I probably would have put like a switch right here, but anyway, so that's the way the problem was presented. Okay, so going through our steps, what are we going to do before we bring up the next page? We're first going to determine the initial conditions, and then we're going to make a replacement. So all of the variables, the little I and the little v, are going to be replaced with I of S and V of S. The capacitor is going to be replaced with a capacitive impedance and an initial condition source. The inductance is going to be replaced with an inductive impedance and an initial condition source. And the current source will be replaced also with its Laplace equivalent. So the current source looked like 24 U of t, and so when we transform it, it's going to be 24 over S. I really don't like that they kept this in milliamps, but we'll leave it like that. I think they correct their units on the next slide. The capacitive impedance transforms to a capacitor, and so what I want to point out here is you note that in this particular case, instead of a capacitor in series with a voltage source, they selected to put the capacitor in parallel with a current source. Now, why would you do that? Because, I told you earlier in a lecture that it makes a lot of sense to always, when you transform capacitors, put them in series with a voltage source, and that is true. So had I been working this problem, I probably would have done the capacitor in series with the voltage source first, then done a source transformation. But why would you want to do that? Well, you'd want to do that because if you do this, then you have everything in parallel. And so you have a single node circuit, which is going to be significantly easier to solve. Here is the inductive impedance in parallel with its inductive initial condition on the current source, and then here's the resistor. So you've got quite a bit going on here in this circuit. You've got a lot of elements. I think the easiest thing to do is just to put a reference at the bottom node and write a node equation at the top node, which I believe is exactly what they do. Okay, so I'll go ahead and show this slide so that you can see step by step what they did. Here's the calculation of the inductive impedance. Here's the calculation of the capacitive impedance. Here is the current source in parallel with the inductor. Here is the voltage source in parallel with the capacitor. Once again, you can get these formulas from the table that shows the different circuit arrangements, and so that's how we got the S-domain circuit shown in the previous slide. Okay, now what's done is we're skipping the initial and final values theorem step, and we're going to go straight to, how did I miss the equation? Okay, so somehow this thing keeps skipping slides. Okay, so the next thing that was done is those three parallel impedances. So here's the inductor, here's the capacitor, here's the inductor, here's the resistor. They're all combined using a parallel combination to get an equivalent impedance, which is given right here. The voltage is done. In this case, they combined the three parallel currents and multiplied that by the impedance. So these are the three parallel current sources added together algebraically. Here is the impedance. So we're just using Ohm's law. I probably, in all honesty, would have written a node equation because I think it would have been just as easy. But this is fine. There's no problem with this. So let's go back and look at our circuit. We had three current sources, all in parallel. So those were added algebraically, meaning this was positive, this was positive, this was negative. We have three impedances in parallel. Those were combined in parallel. And then we ended up basically with a single current source and a single impedance so we could find the voltage. Okay, so here is our equation for that voltage. So what we need to do is take the inverse transform of this expression. So we'll skip the initial and final value theorem step. And so the partial fraction expansion in the denominator, that turns out to be a perfect square. So when we have a partial fraction expansion of a perfect square, remember we have a term over the or double root, we have a term over the s plus 40,000 squared, and then we have an s plus 40,000 term. So when you do that and you take the inverse transform of each term, you get the following. Now, if you need assistance doing this partial fraction, you can contact me and I'll sort of step you through how this was done. But you can watch the videos from last week, and there should be an example of one that was done that had a square in the denominator. You can also use MATLAB on this, and on the next, I think on the next example, I did show a little bit of MATLAB code for how to do the roots, which I think we also went over in your last project. So you should have all the tools you need to get from this step to this step. And then it's just a matter of taking the inverse transform. Okay, so so that gets the voltage. Now, if we go back here, let's go back to this circuit. So what we just solved for is we just solved for this voltage. So now that we have this voltage, we can actually find any of these currents that we want to find. So that's a pretty convenient deal. Okay, so that's a couple of examples. I want to do one more, but I want to end the video here because I don't want these videos to get too lengthy.